guess the nth term formula, and unless you're told otherwise, it's going to be an explicit formula, not a recursive formula that you're looking for. Can you guess the formula for AN with outputs 3, 7, 11, 15, so forth? Well, do you know? Let's start a little more basic here. Do you notice the recursive formula here? Do you notice how to go from one term to another? If you think about it, our human brains think recursively better than they think explicitly in terms of those formulas. Because you can see a pattern, and the pattern recognition, that's recursive thinking. That's your superpower among all the other creatures on Earth, is being able to think abstractly in general, and specifically being able to think recursively and recognize patterns, pattern recognition. I know it's not a cool superpower when you compare it to flying or being able to manipulate metal, with your mind, or turning green and smashing things. But it's what you got. It's your superpower, like it or not. So what's the pattern here to go from one term to another? You add 4, right? You notice that there's a common difference. Oh, here's why I can't see what I'm doing. You notice there's a common difference of 4 to go from one term to the next term. So what would the next term be? 19. So 19. Now, that's a recursive formula you just came up with, right? Because you take to get the nth term, you take the term that comes before it and you add 4. That's great until you want the 1,000th term and you don't have the ones in between, right? So we need an explicit formula if we can come up with it. Any ideas?
4 minus 1.
Yep. So how'd you come up with it?
Just thought about it.
Or and then you guessed a little bit, and there it is, right? Here's one way to come up with it that will work every time when there's a common difference between each successive output. Well, think about it. To go from one term to the next, you're adding that common difference of 4, right? Repeated addition of 4. Oh, that has to do with multiplication by 4, doesn't it? So you can take that common difference, multiply it by n, and then adjust. You know this isn't going to work because you plug in 1 in here and you get 4 popping out. You need 3. Make the adjustment. Oh, if I subtract 1, let me try it. If I plug in 1, do I get 3 popping out? I do. 4 times 1 minus 1 is 3. If I plug in 2, do I get 7 popping out? Yeah, 4 times 2 minus 1 is 7. If I plug in 3, I do get 11. And so you know that works. There's other ways to think about it too. You could graph the ordered pairs associated with these outputs. So you could graph the ordered pair 1, 3, 2. This is A2, but graph the ordered pair with input 2, 2, 7, 3, 11. Just graph those as points. Very quickly, you'll see the slope between the points. You get a straight line of points. Very quickly, you'll see that you have the same slope between any two pairs of points. That slope will be 4, that common difference. And then you can just find the equation of a line. That works too. Okay, so there you go. Any questions on that one? All right. So we have outputs -1/2, 1/5, -1/10, 1/17. Well, forget about the alternating negative. We'll talk about how to handle that in a second. So it alternates from negative to positive, negative, positive. Forget about that. If it weren't alternating, what would the numerator be? If it weren't alternating, the numerator would just be 1. So now concentrate on the denominator, 2, 5, 10, 17. I'll bet you can get a recursive formula for that pretty easily. But we're looking for an explicit formula. And you really can guess on this. It's fun to guess. Unless you can't get it, then it's frustrating. So you're going to need a function in that denominator, a formula in that denominator, below that 1 right there, that increases, not in a linear fashion, right? Because there's not a common difference between 2, 5, 10, and 17. Yeah, that'll work. So we haven't taken care of the alternating, the negative yet, but Do you guys see that n squared plus 1 would work there? Thinking of just the denominator, plug in 1, you do get 2. Plug in 2, 2 squared is 4, plus 1 is 5. Plug in 3, 3 squared plus 1 is 10. Yeah, it works. It works. And then how do you get the 1 to alternate between negative 1 and 1? So you could do negative 1 to the... We want the first term to be negative, so the exponent needs to be odd to start with. So just n would work, right? So think about it. Now just look at the numerator. If you plug in, so you're trying to compute the numerator in A1, for instance. If you plug in 1, certainly you do get negative 1, right? Negative 1 to the 1 power is negative 1. But if you plug in 2, for that numerator in A2, you want positive 1. If you plug in a 2 here, is negative 1 squared? Yeah. And then if you plug in a 3, is negative 1 to the 3rd power negative 1? Yeah. And then so, you know, when n is even, you'll get the positive 1 in the numerator. When n is odd, you'll get the negative 1, so it works. So that'll work. One interesting side note, recursively speaking, how do you generate the denominators? 2, 5, 10, 17. Is there a pattern between each successive denominator here? So I'm just speaking of 2, 5, 10, 17. What did you add to go from 2 to 5? What did you add to go from 5 to 10? What did you add to go from 10 to 17? So what would the next denominator be? Without looking at that formula, what would you add to get the next denominator? 9. Whenever you see that pattern of adding successively larger and larger odd numbers, n squared is going to be involved. It just is. So think about it. Just 1, 4, just think about the perfect squares, 9, 16. That's where that pattern originates, right? To go from 1 to 4, you add 3. From 4 to 9, you add 5. From 9 to 16, you add 7, and so on and so forth. So, you know, it's something to grab a hold of at least, right? Okay, so an, negative 1 to the n over n squared plus 1.